I'm Landau-Lifschitz-Gilbert principal.
Okay, hello everybody. I'm not from Berlin, I'm Portuguese. I'm presenting the results of my master's studies. This is a joint work with my master thesis advisor, Anabela Cruzeiro, okay? And, well, in the next 30 minutes I will try to decode the title of this talk, forward-backward STEs, asymptotics and the large deviations principle, for people that never seen this kind of things. Huh?
Mike.
What? I was trying to avoid it, but okay. Use it. Okay. Just to start, something that is familiar to us. Okay. I'm writing the Schrodinger's equation just to motivate why I studied forward-backwards STs. Okay, this is the well-known Schrodinger equation, which gives us the motion of a particle in Rd under the influence of a certain conservative force given by this potential V. Okay, and it is well known that in 1948, Feynman gave us a formal representation for the solution of this problem. Okay, I'm trying to write here the solution. And this is really nice because this object doesn't exist properly, right? Okay, let's try to decode this. This is a kind of an integral taken in the space of the continuous functions with values in Rd starting at x, the well-known Wiener space. H is the Planck constant, okay? And this thing here is the symbol to the non-existent infinite dimensional Lebesgue measure on this space. Of course, we don't have Lebesgue measure on this space because we don't have invariance by translation, so we need to replace it by our good Wiener measure. So, why I'm taking all this? Because I am trying to motivate you to recover the Feynman-Kac formula, which is presented by Kac. If you consider imaginary time, your Schrodinger equation is, if you take the constants equal to 1, this equation. And this is the famous heat equation which we are talking about 1 week, okay? Well, for this equation, in 1949, gave us a probabilistic representation, not given by this thing, but given by this conditional expectation from a certain Brownian motion that starts at x of a certain function of Brownian motion. This is phi. Okay. And by the way, this is why I fall in love by stochastic analysis. This is the well-known Feynman-Kac formula, which gives us the bridge between stochastic analysis and PDEs, deterministic PDEs. And this is really nice. For example, if you have phi positive, you obviously conclude that our solution is positive. And these kind of representations are really nice for people from numerical analysis. Why? Because you have here the additive property of expectation. And I heard specialists about parallel computing that you can split up to do numerics your expectation and do numerics in several computers and in the end join and add, okay? Like in primary school. Of course, it's not like in primary school. Of course, this gives us an alternative for so complicated methods such as finite element method, which can blow up in the discretizations of the domain. And how I get forward backwards in this picture? Because forward backwards SDEs are a kind of way of trying to get Feynman-Kac formulas for a huge class of nonlinear PDEs, okay? Of parabolic nonlinear PDEs, as we will see. So, first of all, what is a forward-backward SDE? Oops. Well, let's try to think about Tito calculus. Ito calculus is a really nice calculus, but has several limitations. For example, consider this problem. This is a really innocent problem that is presented in a really good book about this subject, My Young, Forward Backwards STs and their applications. I think that's the title. And with this example, we can understand what is a BST. This is an innocent terminal value problem, right? But I cannot say that because there are too many specialists of stochastic analysis here. But I dare to say that the thing that in certain sense defines Ito calculus is the requirement of adaptiveness, okay? Why? Because if we are in the deterministic world, obviously, if C is constant, this is the solution for the problem. But if we are in a probability setting, if we have our familiar probability space with a certain filtration, this is P, right? Probability measure. This problem could not have a solution. Why? This thing, which is not, if we think about this terminal condition as a random variable, okay, L2 and measurable to the terminal sigma algebra, why we have measurability of this random variable in all the filtrations? We could not have it, right? So, in the Ito picture, we could think about the, well, we have a random variable, let's adapt it. How to adapt a random variable? Taking the conditional expectations, right? And then we recover a martingale, and we can use one of the main tools of stochastic analysis, martingale representation theorem, and says that exists a certain process Z, L2, and measurable to respect to the filtration. A little remark, the filtration needed to be Brownian to do that. In such way, we have that our process is given by this integral. Okay. And then we can say, of course, we can put here capital T if we are thinking on a certain time interval. And here T, and here T, and here capital T. And so we can think about we can derive a SD for this object in this way. And this will be the best way to look at a backward SD. Why? Because this new process that we introduced here, the process Z, will be responsible to adapt the stochastic process Y. Okay? So now I'm ready to present you what is a forward-backward ST.
You better be careful with the filtration.
The filtration Brownian. The filtration needed to be Brownian, yeah.
Brownian augmented by...
Augmented by the null sets, yeah, thank you. Okay, so what is the forward-backward ST? Is a couplet system, or decoupled, because in the beginning of the studies of these objects, for example, I think the first one we studied was Bismuth in the 70s. In the framework of stochastic optimal control, because if you want to do stochastic optimal control, you recover a BSD when you have the adjoint equation. But here I will consider a fully coupled system of Ito's diffusion, a usual SDE, and a backward ST. And what I want to remark is that my system is fully coupled, in the sense that the drift of the forward diffusion depends on the backward process, and the driver, this thing here in the literature is called driver, depends also on the forward diffusion. I do not put here dependence on Z because I want to avoid problems of non-uniqueness. If I put here Z on the diffusion coefficient, I could have non-uniqueness for this problem. And what is the framework that I'm going to work? The usual. I'm going to take a probability space with a filtration, which is Brownian, augmented with a collection of the null sets, and I am searching for a pathwise solution that solves this forward-backward system with some kind of integrability conditions, okay? And what brings me here is putting a small epsilon here. So the problem that I'm going to consider is that one, is to put here a square root of epsilon and see what happens to this system when epsilon converges to 0. do not be afraid of this terrible notation, but here I only remark the dependence of the system on the initial time, the initial condition, and on the epsilon, okay? What are the, well, I need to some kind of integrability conditions for these objects. And the spaces that I'm going to work are these two spaces, S2RD, the space of the continuous adapted processes, which is a Banach space with the norm given by this expression, and H2, the space of the adapted measurable processes, which is a Banach space given by this expression, okay? Okay, and it's better to write the equations on the board because I don't know if I will keep the time, and I would like you to remember the main ideas. Okay, the equations are this, right? Why? I need to be careful. And I have one initial condition to x and one terminal condition for y, which is that one. Okay, now my problem is what happens when epsilon converges to 0. First of all, to study this problem, I need to know some kind of results of existence, uniqueness, or and regularity as usual, right? So if I have the classical framework of Lifschitz continuity, I know that there exists a solution x epsilon, y epsilon, z epsilon, that solves pathwise these creatures, these equations, okay? On that space that I'm taking, MC, which is clearly a Banach space with the product topology that I'm considering. The solution will be denoted like in the blackboard, x epsilon, y epsilon, and z epsilon. And where I have the connection between these creatures and the deterministic PDEs in the following theorem that you can find in a paper of Delarue in 2003, which says the following. I can think in the backward process and evaluate it on the initial time. By the magic of probability theory, using Blumenthal 0-1 law, this will be a deterministic function. So let's give her a name. Let's give it a name. U epsilon. And this function solves in a certain sense, if I don't have more regularity, this PDE, okay? This is a quasi-linear parabolic PDE. You have here the structure of the infinitesimal generator of the fourth diffusion, right? You have here non-linearities, and in the semi-linear part, you encode non-linearities for this equation up to the derivatives of the function. This is really nice. We are giving a probabilistic meaning to a huge class of parabolic PDEs, right?
There's a capital X, right, in the U.
Where?
That means the U epsilon T capital X.
Capital X?
Yeah.
No, I'm evaluating on the initial condition.
Yes. Start with little x,
Yeah.
but then your left side is a process, and then that should be a capital X.
Oh, capital X. Thank you. But sorry, Ong. As you can see, this process on the initial time is x, right? Because
But this you evaluate at little y little s, right? You evaluate at time little s.
little t.
Yeah, little t to little s.
Yes.
Yes.
And if you take here this expression.
Oh, I'm sorry. It's y little t to little t. Okay, I see.
Yeah.
Yeah.
If you say this, of course, this recovers the initial condition, x. Okay, this is. Okay, and if I have more conditions, for example, if I can differentiate, I can say that my function will be a classical solution in the sense of C1 to functions, C1 to respect to time, C2 to respect to space. Okay, this can be done using four-step scheme methodology that you find in the book that I mentioned, which is from Ma, Proter, Young. Okay, and this is a really nice method, for example, to implement numerically And it is done with the help of deterministic PDE literature that you find in the classical book of Landau-Lifschitz-Gilbert, quasi-linear parabolics of second order, I think. Okay, how this connects, for example, to hydrodynamics. If you take the drift of the forward diffusion being y, the dimensions k equal to d, and sigma be the identity matrix, you recover a backwards Burger's equation. And if you do, of course, canonical time reversal transformation, you recover your backwards equation. So these kind of tools can be used to give probabilistic meaning to a simplified model that everybody knows, Burger's equation, for turbulence, that describes the motion of a flow with viscosity parameter epsilon over 2 under the influence of this external force. Okay, I only want to remark that Anabela Cruzeiro has some works about the extensions of these forward-backward formulations for Navier-Stokes equations. I'm not doing this here, but it's kind of natural to consider the same formulation for Navier-Stokes equations, but your processes will not live in the Euclidean space, but will live in a Hilbert space that encodes the condition, for example, the condition of the divergence free field. Okay.
Up to this point, you had U scalar, right? Now U becomes a vector in this page. Yes.
U is always a vector. The forward diffusion is k-dimensional. The backward one is d-dimensional. No, it's the opposite. Sorry, x d-dimensional, y k-dimensional.
You get a system.
Yeah, this is really nice because viscosity theory, for example, is done more for scalar case. And here I gave you a viscosity solution in a vector, system of PDEs, right? Okay. So first of all, let's consider the usual hypothesis to do something. If we take our coefficients be Lifschitz continuous, okay, monotone with respect to x and y, this is the property that we need. Of course, this will have consequences, linear growth for some constant, and these two mappings as continuous mappings. And what we can say under this framework, we can have the following result. Using a fixed point Banach argument, we can construct a solution, from little t to capital T for a small time enough time duration. Okay. Using only a fixed point argument. If you want to all the time, On can tell you more, you can do it via four-step scheme methodology. And the magic of these systems is that the backward process is really a function of the forward process. And this process decouples immediately your system. This is what I'm saying here in the first result. The backward process is almost surely a function of the forward process. And I have a bound almost surely and almost everywhere in the time interval that I'm working for the control process. Okay? And this bound, if you do the computations, for example, if you pick the paper of De La Rue and put epsilons everywhere, you can see that this bound is not dependent on epsilon. Okay? By conclusion, we can say that we have continuous versions of the process y and z, for example. But if I have more regularity, for example, sublinear growth of these guys here, uniform bound for the diffusion coefficient and for the terminal condition, the matrix A uniformly elliptic, okay? And if I can differentiate, this is a really classical setting. I have the following results. I have that my family U epsilon is uniformly bounded in epsilon, is actually a C12 function bounded, and I can give a bound to these gradients, okay? But this is a very particular case. And in this case, I can give a full description for the control process, given by this way. By square root of epsilon times the gradient of U epsilon times the matrix. Perhaps it seems it misses a transpose, but at this stage I'm terrible with linear algebra. And for people that are really fans of probability theory, all of these can be proven probabilistically, okay? For example, this free can be done with the use of Malyavan calculus. This is really difficult, in my opinion, because Delahaye spends one paper of 70 pages doing it. It uses a kind of Bismuth-Ellsworthy formula of integration by parts formula that Talmaye, son-in-law of Malyavan, used it to derive interior estimates for linear equations in compact manifolds. But for people that love geometry, this is really nice.
So before you, 3.5, you point out that it's independent of epsilon. So it holds as a take epsilon over 0.
Yes.
Now the big T, the time interval is it can be kept.
Thank you, because I forgot to remark that. If you use the Banach's point fixed theorem, your T, where you are working, the capital T will not depend on epsilon 2.
Yeah, and the initial data you can. So K1 is not dependent on initial data either, or maybe it's one of those parameters.
These bounds that I'm giving only depends on the sublinear growth constant of the coefficients, not with epsilon, without epsilon, on capital T, but with my fixed point argument, I can see that capital T doesn't depend on epsilon 2, and only depends on these dimensions and on the Lifschitz constant. It's a really good exercise, it was for me, doing epsilons everywhere and see what happens, okay? And with these results, I can cook up a simple result of asymptotic behavior. In some sense, I am allowed to pass to the limit, okay? So, what is expected? What's expected is when I put epsilon to 0, I recover a system of ODEs, and that's what I'm going to have in the limit. Why? Because in this framework, the Z process is bounded and converges to 0, okay? But after a conversation which was really fruitful with Professor Adi Murphy, I realized that I can relax and I don't need these three conditions to pass through the limit. I can use more sharper inequalities using, I don't know if you are aware of BMO martingales, okay? But I am too tired these 2 weeks to do it. I have homework for vacation. So, the first result is that our system of forward-backwards SDEs converges to this limit system of ODEs. The second result is that if you take the limit function in epsilon, your limit function will be a viscosity solution of your limit PDE. And I can say something about the regularity of this limit function. Is bounded, continuously Lifschitz in X, and uniformly continuous in time, and more. This is a kind of, I don't want to say it, but this is a kind of academic hypothesis. Why? Because if I assume that the limit function has regularity enough, and if I assume uniqueness of solution for this system, I can say that my limit function solves, in the classical sense, this PDE. For people which are more familiar with PDE, this is not really interesting. Why? Because this system is the characteristic system associated to the hyperbolic PDE that I presented, okay? And
before you go to this, can you go to the previous page?
Yeah. No? This one?
The previous one.
Previous. This?
No. Keep going, because you had this quasi-linear PDE.
Oh, I know. This one.
This one.
Hyperbolic.
Before going to the point 4, the equation 3.8, as it is, the regularities you put there doesn't incorporate shocks.
No, because I am, as I said, I am working on a really particular case. Everything is smooth. I can pass to the limit, and if, for example, and the limit is in viscosity sense. Okay, I only have limit in classical sense if I assume uniqueness of this ODE system. Okay. This is a kind of bridge between these results and the oldest method of characteristics, which was exploited in the 19th century, right?
Yeah, the question I was perhaps is that unless you take cap T very small, you may not find smooth solutions. It has to have sharpness. That was the point. But we can talk about it later.
Yeah, but I think the problem is not capital T, it's the differentiability properties that you can assume to have smooth solutions. Because in these computations, if I want to differentiate it somewhere. So I'm using a particular setting where these results are available. These don't cover, for example, Berger's equation. But if I forgot this, I can pass to the limit in viscosity sense, and it covers the Berger's case. That's why I was thinking 1 week ago when I talked. Okay. The outline of the proof, I'm not going to bother you, but the outline of the proof relies on this a priori estimate, this kind of estimate, energy estimate that I can do. And my strategy was to prove that x epsilon, y epsilon, z epsilon forms a quotient sequence on the space that I'm working. This is more or less easy if you know Burkholder-Davies-Gandhi's inequalities, if you know Dub's submartingale inequality, if you know Ito's isometry, you cook up and you can pass to the limit. So, since everything is bounded, I can see that my limit process x, y, and 0, do not forget that z is square root of epsilon times the gradient of u epsilon times sigma. Sigma is bounded, gradient of u epsilon is bounded by Malievan calculus, you can pass to the limit. And x, the limit process solves this equation, and the backward solves this equation, which is the same to say that I have a solution for the system of ODEs, right? Okay, next conclusion. Next conclusion relies about the regularity of the function, the limit function u. I can cook up this estimate. And this estimate says that u epsilon forms a family of equicontinuous functions on compact sets of 0t times rd, right? And I cannot forget that u epsilon is a family of uniformly bounded functions. So I can use the Arzelà-Ascoli theorem, which we heard about a lot here, and say that u epsilon converges to u, the limit, uniformly in compact sets. This is the nice property that we want to handle with viscosity solutions. Why? Because u epsilon is a viscosity solution of a certain PDE. U epsilon converges to u uniformly in compact sets. So, using, for example, user's guide of Landau-Lifschitz-Gilbert, we can pass to the limit. U is actually a viscosity solution of our limit PDE. Okay, viscosity solutions property, it's okay. And if we take this inequality and pass to the limit, we recover that our limit function u is uniformly continuous in time and uniformly continuous in x in compact sets too. The last property, the artificial one that I cooked up. If I have uniqueness of solution for the ODE system, okay, what can I say about existence of solution, smooth solutions to the limit PDE? Well, I can take V, a C11 function bounded, okay, and I can think about this function here. If I differentiate, since I have all the regularity that I want, and use uniqueness of solution for my system, I can conclude that V is actual to U. So, where V is the solution of my quasi-linear PDE. So, U is actually a solution in classical sense for the limit PDE that I was talking about. So please let me talk a little bit of large deviations, okay? The second property that I can do here is establish a large deviations principle. For people which are not from stochastic analysis, a large deviations principle could be might scary in the beginning. But it's a kind of statement that encodes in certain way the exponential decay of probability measures of what is a rare event. What is a rare event here? A rare event here is that our system go away from the limit ODE, right? So this is the framework of Friedlein-Wenzel estimates. Okay. And what will be the key to build a large deviations principle? This property. Because this property is really nice. If I use this property, I have that my forward diffusion, my forward drift, is actually a function of x epsilon. And here, I have that the diffusion coefficient is also a function of x epsilon. So for people which are familiar with Friedlein-Wenzel theory, I can apply Friedlein-Wenzel estimates to the forward diffusion. And now, the good news is that I have regularity enough to use the contraction principle to pass the large deviations principle for the laws of this process for the for the laws of the backward process. This is really funny. And first of all, just state the theorem. In these ideal conditions, when I have uniform convergence of the drifts and the diffusion coefficients to a certain limit, uniformly in compact sets, I can cook up a large deviations principle for these, for the laws of this STE, and cook up a large deviations principle is giving a good rate function, lower semi-continuous function with level sets which are compact, okay? And having a large deviations principle is having these bounds. I'm really sorry because I don't have time to explain, but if you play a little bit of perturbations of ODEs with epsilons, you can see that by using the reflection principle of Brownian motion, that the probability of Brownian motion goes away of a small ball of radius delta is of exponential decay. So this is why it appears here, logarithms and things like that, okay? Okay. So I use this theorem to the forward diffusion, and now I need to pass the large deviations principle to the backward one, okay? What I'm going to do is use what is known in large deviations theory as contraction principle. Okay, large contraction principle, the contraction principle that I'm going to use is the following. If I live in a certain topological space, topological vector space, and if I have a family of probability measures satisfying these creatures, large deviations principles, I can transport the large deviation principle for the transported probability measures, okay, if I have a certain family of operators and I can transport these probability measures and the LDP for this space here with this good rate function. I do not have too much time to explain, but I can say what is explicitly here the F epsilon that I'm going to take. Can I write here? Okay. It's really easy because the contraction principle that we will use relies on a certain family of operators that we were dealing on the first result. Since we are playing with the functions u epsilon, the family of operators that we are going to consider here is the following. We take a certain function in this space and evaluate like this. And I have the regularity enough to say that F epsilon converges to F, which F is without epsilon, uniformly, okay, in compact sets of this space. And I have the regularity enough to assert that F epsilon is a family of continuous operators. This can be done, and it's not so much difficult. I only wanted to state this, and I think it's all. Thank you.
Out hold if the FBSDE has only the weak solution, unique weak solution.
Unique weak solution? Yeah. That's my question. I don't know any results of large deviations for weak solutions. I have a philosophical problem with this.
Weak solution of which equation?
Martingale solution. Of this system.
Concerning backward problems, there is a person, student Zah. And he writes thousands of papers on both backward equation and on large deviations. So in a sense, it seems likely that he has also written a paper on joint subject. Have you ever seen?
No.
I don't know, I'm just asking because he really writes on both subjects.
But before trying to handle the problem, I did a good search on MathSciNet about large deviations, and
I'm just asking.
I didn't see it.
So let's thank you again.
Thank you.
So thanks for the organizers for giving me chance to talk here on this shell model of turbulence with Levy noise, existence, uniqueness, and large deviations. So I'll give. So this is my outline of my talk. So first I'll give the introduction on shell model of turbulence. So then I will give functional settings, and also I will go for some basics of Levy process and then extends the unique result. And the main thing is our large deviation principle. There I will give the large deviation principle for our system. So first I will give the introduction. So GOI model, larger Yamada GOI model is a special kind of shell model. It's a Navier-Stokes equation written in the Fourier space, and where the interaction between different modes is preserved between nearest modes. We are taking only the nearest modes that you can see here. So here we are considering GOI model. This is a one-dimensional cascade of energy among infinite sequence of complex velocities. UNT are complex velocities of one-dimensional sequence of wave numbers. Here Kn is K0 2 raised to n, and 2 is that we can change also. And this is called n is called the shell index, and you can write the equation in this form. Here, as you can see, we have to choose this u minus 1 and u naught as 0, and un star denote the complex conjugate of un, and nu is this term is the kinematic viscosity, and we have to, because of conservation of energy and all, we have to choose a plus b plus c equal to 0. So this is the model, and we have to rearrange the same model into our usual framework. That is our aim. So we have to define the bilinear term, linear terms and all, and we are adding noise here also. So that is our aim. So let me define first the functional setting. So H is the Hilbert space I am taking. H is a space u equal to u1, u2, etc. C infinity functions with the summation mod un square is finite. So that is our Hilbert space H. And here I am defining the inner product as real part of summation un vn star, and the norm here is defined like summation mod un square raised to half. So this is our EH space, Hilbert space H, and I am going to define V. V is the space of all the functions from H which has this quantity, that is this property, that is summation n equal to 1 to infinity kn square mod un square is finite. So that is our space V, and it is also a Hilbert space. You can prove that it is a Hilbert space with the norm defined by this to the power half. So summation mod kn square mod un square to the power half. And now let us define the linear operator. So we defined the spaces H and V. So the linear operator A is a positive self-adjoint operator defined by AU equal to, in this way, AU1, AU2, etc. Where AUN is, we can see kn square un, that we already seen from our equation, and the domain of A is defined like is a Hilbert space is the norm defined by norm of u under dA is equal to summation equal to 1 to infinity kn raised to 4 mod un square to the power half. So that is our linear operator A. And A raised to half u, you can see here A un is kn square un, and A raised to half u will be k1 u1, k2 u2, etc. And we define d of A raised to half, domain of A raised to half as set of all u1, u2, etc. such that kn square mod un square is finite. And you can, before we have defined V in this way only, the same space. So we can identify V with d of A raised to half. So V equal d of A raised to half, and its dual we can see V dash equal to d of A raised to minus half, and it's a dual space of V. And also we are like in the Gulf triple, we can see in the Navier-Stokes equations. So V subset of H I can identify with the H dash, and is subset of V dash. V dash is a dual space of V, and this is our linear operator. Now we have to define the bilinear operator. So let us define the bilinear operator in this way: B of uv equal to B1 uv, B2 uv, etc. Where B and uv is defined in this way, and we are choosing A, B, C in such a way that A plus B plus C equal to 0, and this is a special kind of A plus A, B, C. So we will get B and uv equal to this term. And in a one more way we can define, if you take a orthonormal basis of H, En, then we can define B uv in this way also. Summation you can see here. So this is our bilinear operator B, and now so this bilinear operator satisfies these properties. So this is easy to prove all these properties. Mod BUV is less than or equal to C1 times, that is a continuity property, and then mode u v is equal to C1 times norm u in norm mode v. This norm means I'm putting norm for v norm and modulus for h norm. So for and secondly, this mode b u v under v dash is less than or equal to C3 times mode u mode v. These are all the properties we can prove easily. And this, as we see in Navier-Stokes equation, we will get bu v will be equal to 0. So that also we can prove in these equations. So b is a bounded linear operator. This v norm also will be less than or equal to this quantity. So all these quantities we can prove easily for the as the properties of bilinear operator. Now coming to the stochastic model. So first I will define what is a h-valued ft adapted linear process. So a stochastic process Wt is a h-valued ft adapted linear process with the covariance operator Q. And you already seen in the morning of process synthesis lecture that what is Rice class operator and all these things. So for each non-zero h, this quantity q raised to half h inverse Wth is a standard one-dimensional linear process. And Wh is a martingale adapted to Ft. And expectation Wt equal to 0 and covariance of Wt is exactly equal to Tq. And you have to remember this space. This is important space because we are using h0 space in our calculations. So h0 space is q raised to half h. And h0 is equivalent with the inner product given by q raised to minus of u and q raised to minus of v for all uv belongs to h0, where q raised to minus of is the pseudo inverse of q raised to half. And LQ is the space of all operators yes, such that SQ raised to half is a Hilbert-Smith operator. And this you can see that is mod SQ square. That is a norm actually defined in the trace of SQ S star. So that is written there. In the LQ norm is defined in this way. So that is a standard h-valued Ft adapted linear process. Now Levy process. By last week we already heard about Levy process and this all these terms from Professor Bavra's lecture. So here I am giving just the definition. Here I am taking E is a Banach space, but I am working with the Hilbert space H. So in a Banach space E, this is a Levy process if it is adapted to Ft, the filtration, and x0 equal to 0 almost surely, and there's independent increments, that is st minus st is, ss is independent of fs, and it is stochastically continuous, that is probability of as s going to t, probability of xt minus s greater than epsilon will be equal to 0, and the right continuous left limit Cadillac path and also stationary increments. So this is a Levy process. And these quantities also you have already seen, like jump process and all these things. So a jump of xt is delta xt is given by xt minus, and for any subset of E, we can define the number of jumps as n of tz, and n of tz is given by the number of jumps that you can see by this equation. And the differential form is given by n of dt dz omega. And the compensator Poisson random measure is given by n tilde. I am using n tilde symbol. N tilde of dt dz is n of dt dz minus dt lambda dz. This is a sigma finite measure. And dt lambda dz is known as the compensator of the Levy process. And this space is also important. So d of 0 t h I am taking is the space of all Cadillac paths from 0 t into h, where it is a Hilbert space. That is an important space for our problem. And now I am defining HP lambda 0 t cross z f is any separable Banach space. It is like a set of all G that this expectation to the power p is finite. So this is space. So we are working with a space like HP S lambda 2 p equal to 2. We will take p equal to 2 in this case. So this is compensator Poisson random measure. And Levy-Kinsin Ito decomposition will give our Levy process can be written in the form of Brownian part and small jumps and large jumps. So we can decompose into this Levy process into Brownian part, small jumps and large jumps. So now I am coming to the extension and weakness theorem for our model. So by this all formulation, functional setting and formulation of linear and bilinear operators, we can able to write our system as in this way. That is, I am not writing a u epsilon there because I want to get one u epsilon also there. So du here epsilon is there, du epsilon plus f is f forcing. So you can see here epsilon I am putting there, so you can see there sigma tu. So this is the equation into the PDEs. This is the equation with the initial condition u0 equal to u0. So u epsilon is there actually. Now my hypothesis, that is the function C is sigma belongs to CO0 T cross V into LQ H0 H. H0 already I have defined, and G is, this is a space I have told to, because we take P equal to 2 there, so that the integral of T and integral Z mod G square, expectation of mod G square is finite, and this is the linear growth property, and this is the Lifschitz property. So I am assuming all these hypotheses for my framework for the problem. And yesterday also Pani was also talking about this strong solutions. So strong solution U epsilon is defined by a probability space. As it is L2 in omega, and L infinity 0 to H intersection L2 0 to V intersection D. This was the space of all parallel paths. Valued adapted process which satisfies the GOI model. So exactly I have written here in the weak sense, and suitable energy estimates. So energy estimates like we can prove. I'm not including the this. If you take the Galois approximation down, something 2 nu times less than or equal to some constant. So by that also you can prove. So energy estimates we can prove. Under the suitable energy estimates we can prove. This is the definition of strong solution, and extends and uniqueness result for the strong solution. So for expectation mode is node square finite, and f belongs to 0 to v dash, and by suitably choosing epsilon smaller, so that and also the diffusion coefficient satisfies our hypothesis, we can prove that this our u epsilon will belong to L2 omega d0 th intersection L2 0 to v, and I am adopting the method of Professor Sri and Sundar, like local monotonicity methods. So I take this operator f of u minus au v of uu as or nu times. So this is my operator f of u, and I will prove that f of v is locally monotonic in some L4 ball, and after that by using Mindy-Broder method I can prove the existence and uniqueness result. So that is the existence and uniqueness result. So we can prove the by taking f of u equal to in this way, locally monotonic, and by using the Mindy-Broder method we can get the existence and uniqueness. So this is the first part, existence and uniqueness result for the shell model. Now I am coming to the large deviation principle. So I think all of you heard about large deviations, and Andre gave something on large deviations. So I am taking here a Polish space x. X is a complete metric space, complete separable metric space, and a function I from x to 0 infinity is the rate function if it is I is lower semi-continuous, and if it is a good rate function, if for arbitrary m in 0 infinity the level set km such that a set of all x such that ix less than or equal to m is compact in x. Remember, x I am taking as a complete separable metric space. And now the definition of large deviation principle. So a family of probability measures p epsilon greater than 0 satisfies the large deviation principle with a good rate function I, satisfying these two conditions for any closed set f, limit supremum of epsilon log p epsilon of f less than or equal to minus infimum of I of x, and for each open set G, limit infimum of epsilon log p epsilon of G greater than or equal to minus infimum of Ix, x belongs to G. This is the definition of large deviation principle. And I am coming to Laplace principle, because I need a Laplace principle also here, because I am working with the Polish space. So in Polish space, Varadhan, Bryce, Lemma is there. Like in Polish space, Laplace principle and large deviation principles are equivalent. So I can use instead of Last division principle, I can prove the Laplace principle also. So Laplace principle is for any continuous bounded function in 0, 1, limit n tends to infinity 1 by n log 0, 1 e raised to minus n h of x dx is minimum of h of x in 0, 1. And so Variance lemma is like x is a Polish space, and if u epsilon is a family of x valued random variables, that is a Last division principle with the rate function I, then this satisfies this set u epsilon satisfies Laplace principle on x. And Briggs lemma is the Laplace principle implies the LDP with the same rate function I on a Polish space Ex. So both of these are equivalent. So we can, instead of Last division principle, we can prove the Laplace principle also. So now I am coming to my model. So
you define Laplace principle on 0, 1, but you use it on a general Polish space.
yes, sir. I am using it as that I give it as a definition only, just for understanding what is Laplace principle.
Yeah, but the Laplace principle by Baradan space. So that should involve the rate function I of
Yes. Yes. Yes, sir. So now I am going to define the spaces needed for my formulation of the problem. So I am taking that red colored space that is important for us. So we are defining that space. So Sn bar, I am defining Sn bar of n as Sn tilde. So it's the usual product topology we are using there. Sn tilde bar cross Sn, and I am defining what is Sn tilde and Sn. So Sn tilde of h naught is defined set of all L2 valued functions from 0 to h naught such that Lt tilde is less than or equal to n. So you can see there Lt tilde of psi is integral half times integral 0 to t norm of psi of s naught square ds, and this 0 norm I have already defined in LQ space there. So remember that one, Lt tilde of psi is defined in this way. And Sn tilde is defined like a set of all psi such that this Lt tilde psi is less than or equal to n. So controls I am applying. Now I am coming to Sn. This set. So this is already defined. I am coming to Sn. Sn is a set of all phi such that Lt phi. This also you have to remember. Lt phi I am defining. It is integral 0 to t integral over z L of phi of t z d lambda of dz. So this quantity is less than or equal to n. Set of all phi such that this integral 0 t integral z L of phi of t z omega lambda dz dt is less than or equal to n. So I am taking the controls of phi and psi, and where L is a function, r log r minus r plus 1, so r belongs to 0 infinity. Now un is a space I am taking. I am collecting all these quantities un. So un I am defining set of all u and theta and phi. I am defining phi and psi. Phi and psi. I am collecting all these phi and psi such that u omega or belongs to Sn bar. Sn bar is Sn tilde cross Sn. So un is also important space for us. Now there is a result by Dopis, Buziraja, then Ikeda Watanabe book also contains the result that in a Polish space, if x and x naught are any two Polish spaces, we can find a measurable map that we can represent by our solution. Our solution u epsilon can be represented as a measurable map in this way. So g epsilon of this, in this way we can represent our solution that I already got from our stochastic shell model. So we can represent that solution as a measurable map from this space x naught cross v of h. V of h is 0 th and m of xt. So that I have not defined there. So xt I have defined like xt is 0t cross x. And suppose if you take any compact set subset of x and mu is any measure, we are taking all the measures for which mu of k is finite. So that is m of xt to x, we are defining the measurable map. We can find a measurable map G epsilon, and we are interested in this large deviation principle for u epsilon as epsilon going to 0. So that is the interesting thing we are going to find how we will do that one. So now we have to define our rate function, and SI is, so this for each I belongs to x, we are defining xi as set of all controls. We already defined what is S there. S is like a union of all these. By this as I defined n greater than or equal to 1, this quantity. So set of all phi psi belongs to S such that psi is the initial condition. I am taking initially psi equal to g naught of integral 0 t psi of s ds, and this quantity I will define next page actually. L tilde of phi is nothing but integral over L of phi of sz lambda dz Lt of phi, and I am defining my rate function as sum of these two quantities. We already defined there. You can see L tilde plus Lt. First, this is L tilde and this is Lt, and I am taking infimum over this set Si. And if we will take infimum over empty set as infinity, and these are the assumptions for our large division principle. So first assumption is weak convergence, and the second is compactness. So first assumption says if you take any family of this theta epsilon, phi epsilon, psi epsilon for this under this um I have already defined this set. You can remember this one. Un is set of all phi psi such that this belongs to Sn bar. So I am taking any family of from that one, that set, and if theta epsilon converges in distribution on Sm bar of real valued sum, random valued functions, theta is equal to phi psi, then our map G epsilon will converge to G naught. G naught was I already defined that is psi, and where lambda t psi is this quantity integral 0 to t, interval is I think I have missed that. Interval 0 to t, 0 to capital T dt. So lambda t g is integral 0 to t interval z g of sz lambda dz ds, and this set km, that is our initial conditions we have taken. This g naught, this quantity has to be, this set has to be a compact set. If we have these two assumptions, then there is a result by Busiraja, Rupees and Marolas that if u epsilon equal to g epsilon of this measurable map, and if g epsilon satisfies our assumption, then our family satisfies Laplace principle in X, and since X is a Polish space, it automatically satisfies large deviation principle. So mainly we have to verify these two assumptions. That is the weak convergence assumption and also the compactness assumption. So for our set, for our model, we have to verify these two conditions: weak convergence and also the and also the compactness condition. So first we will prove the compactness theorem. This is our space we have taken. This is a Polish space. This is a D0TH intersection L20TV, that is a Polish space. So I am taking this X as D0TH intersection L20TV, and u theta as is a deterministic controlled equation. So you can see controls here. We are applying controls here phi t and L of phi of t z, and we are applying deterministic controlled equation. We have this deterministic controlled equation with the initial condition u theta 0 psi equal to psi. Then we have to prove this Km. This set is compact. This Km I have taken the whole u theta which belongs to D0T intersection L20TV. Theta belongs to um. You can see theta belongs to and um is set of all controls. You can see here. We are controlled by this set, and Sn tilde was like a set of all phi such that L tilde of phi is less than or equal to capital N, and Sn tilde was set of all phi such that Lt of phi is less than or equal to capital N. So we are controlling these two quantities. So controlled equation is there. Controls are there, and we have to prove this set is compact in X. So as usual, we will take the sequence of u theta n corresponds to the solution of this controlled equation d u theta n plus this equation you can see here, because only one change is like phi n, and L of phi n is coming here, and we have to prove this u theta will converge to u theta in Km for compactness we have to prove, and so we can prove that u theta n converges to u theta in this space. So what you have to do is you take the difference actually. That is a better way. So take the difference. You d u theta n. Suppose you are giving some w theta equal to u theta n minus u theta, and use the properties of A, B, and then the bounds on these terms, this psi n and psi, because we already noted that psi n and psi belongs to this control set. So you can use the properties of control set, and we will get some m or something like that. That capital M will be coming because of that control is there. So we can prove that this quantity, this supreme norm and the L2 norm will be converging to 0 as n tends to infinity. So that is a compactness outline. Now we have to prove the B convergence argument. So for proving B convergence argument, let us define a set theta epsilon equal to, here also we are taking the control from that set, theta epsilon equal to phi epsilon psi epsilon, theta epsilon of omega belongs to Sm bar, subset of um, and it is converging to a distribution theta with respect to the weak topology indefinite in U. Then we have this G epsilon, this mapping has to converge to G naught. That is a question. So whether it will converge to G naught or epsilon going to 0. This was our original equation. If you represent in our ordinary means, if you differential equation, that is our shell model, you will get the deterministic one in this case. So that whether as epsilon going to 0, this will converge to that deterministic one. That is a question. So that also you can prove in this space D0T H intersection L20T V. So we are taking here is a before we took a deterministic control equation. Now we are taking a stochastic control equation. We can see here control is here. This part was completely from our deterministic control equation. Here control is here, control is here. You can see, and this part is our stochastic part, and here this is stochastic part. We are coming here. So it is a stochastic controlled equation, and before as we noted before, we have to prove this u theta epsilon will converge to our equation, that is G naught of this equation, that is given by this deterministic controlled equation. So that also you can prove by taking some w theta epsilon equal to u theta epsilon minus u theta, and by using the properties of this control set and properties of A and B, we can prove the V convergence result also. That is the outline of V convergence. So finally we can conclude that in this space D0TH intersection L20TV, our solution satisfies Laplace principle and hence large deviation principle in X. So X is our D0TH intersection L20T in that Polish space. So this was the result we got by using this stochastic shell model for this. So these are some references. So thanks to my professor. Aisa for thank you, Aisa. Thank you.
The meaning of shell. And the table self again.
What?
What is meant by shell? Is it useful to that picture?
This I just included that. It's not useful to that one.
I have a quick question. Maybe it's a just matter of notation. I guess the description concerned the shell model, but I guess in many of the equations you were writing with something that looked like a full Navier-Stokes system rather than the shell model. Is there a reason for that? For instance, here. So the shell model is basically a non-linear dynamical system.
Yes, sir. It is a Navier-Stokes equation written in this Fourier space.
Which is defined in Rn. Whereas this looks like an object defined in an infinite dimensional space. the left-hand side of this equation.
So it is infinite shell model.
Infinite shell model.
But K, the wave number is discrete here, right?
Yeah.
So there was one slide just before the part concerning the alert deviation, which had the functional setting for this. I wonder if you could maybe scroll back up there. So somewhere I would say maybe less than 1 half into the presentation just before the.
Sir?
Okay. Yes. Okay, this was the no, it's too far.
Back.
Yeah, now move forward a little bit.
Forward.
Yes. Okay. Oh, yes, here. Okay, so H and V were defined initially as the.
There I already defined H and V.
So these are basically like counterparts of L2 and H1, right?
Yes. Yes.
Okay. Okay. Well, that's good. So just a comment on Sri's question. The reason why they call it a shell model is because when they are derived from the Navier-Stokes system, it is done by averaging over all wave numbers lying on a certain shell. That's why they are called the shell models.
Any other question? If not, then let's take a